This is my CNC hacksaw. I built this last winter because I have a project coming up where I need to make a bunch of little miter cuts in aluminum, and this is what this is primarily designed for. Now let's address the gorilla in the room, and before we go down the rabbit hole and all the rest of the stuff here, yes, hacksaws are slow. Compared to a chop saw, miter saw, they're very slow. And in fact, if I'm cutting a piece of steel, square or miter, I'm using my abrasive blade chop saw. If I'm cutting a long piece of aluminum, I'm taking up my miter saw. It has a special blade for aluminum and whacking it right. And it's not a problem and quick. However, the problem comes is that when I'm cutting these small pieces off the end of a piece of aluminum, like I'm taking a square to a miter or changing a miter to the other side, these small pieces of aluminum sometimes can get trapped by the blade and drug into the back, and things happen. I've got pieces stuck in the ceiling. I've ruined blades because when you if you do pinch a piece of wood, it will probably chew its way through there. It may be kind of exciting, but it won't be near as dramatic as this piece of aluminum coming shooting out of there. So yeah, it's very dangerous, and that's why I thought I'm going to build a hacksaw. Now I've tried other ways. I have a bandsaw, and I tried my bandsaw, got a metal blade for the aluminum, and it worked great, although it didn't seem to stay sharp that long as what I really needed for that project. So I thought I'm just going to make this. That way I don't have to cut it. I can just set it up, push the button, and walk away. And that's what I came up with. In fact, my goals on this here. Well, first off, this is it. Before we do the goals here, this is what I came up with. This is a little bit different design than one I've seen before. There's no back. On the back side there are big hinge that raises the whole thing up and down. In fact, the only thing that moves here is this 1 inch square stock. It's been driven by this little wheel and piston type apparatus in the back that just drives the bar back and forth. However, I've constrained the bar front and back with bearings, and what I did at this long bar here is actually my weight that can push itself into the work material. However, I can control how far, how quickly it drops into the work, and even stop it if it's struggling. All the black things you see here are the printing. That's 3D printed. I use PETG exclusively for this project. Um, I did not make it to sit on my bench. I don't have a place for it, but I have a space for it. So I put this on a cart so I can wheel it around when I need it, push in the corner when I don't. And I've probably I've probably cut 30, maybe 40 pieces so far with it, just in the trying out and actually using it a couple times. And I'm really impressed how accurate. And it's not, yes, it's slow comparatively, but really, it's probably a 5 to 8 minute, depending on the piece of material I'm cutting, to cut through it. And like I said before, I push the button, I walk away, and I come back, it's done. And better than that, it's not just done. It actually this is the automatic part. Okay, it cuts the piece, stops the saw, and then raises right back up where it started. That's the CNC part. It needs to know exactly where the blade is at on the height, and so that's why I'm counting the pulses coming from the motor. Basically, so I can count the pulses. I know where it was, then where to return to. Okay, and I save the saw's position when necessary. Arduino Unos have a small EEPROM, not big, but big enough for my purpose here. And so when I push a button at the end of the project before I power it down, I can save its position. Because that's the thing about many CNC units. When you fire them up, boot them back up, they have not a clue where they are. You got to home it. Now I can still home this one. It will home it and back away and establish the position, but I don't need to do that because I've saved the position so it knows where it's at when it starts. It also has a self-adjusting feed rate, because if you think about a piece of aluminum versus a vertical piece, that top piece has a lot more material you're cutting across, and that's going to be struggling a lot more than the vertical piece. And so this can sense when it needs to slow up a little bit, the feed rate, and I can stop that temporarily, and it just takes care of itself. I'm using standard hacksaw blades too. I remember my dad's had a great big thick wide blade. It was those industrial hacksaw blades, which I believe you have to have because most all of these powered hacksaws I've seen are massive, big weights on the front great structures, and they really kind of force that weight down onto the blade to cut through things. Well, if I'm trying that with a lot of force necessary to get through a piece of material, it's probably going to twist these lighter blades, these commercial, non-commercial blades I'm using, household blades basically. Um, and they're a lot cheaper too than the commercial thick big blades. So I wanted to use the regular standard hacksaw blade, and it's been great. Okay, limit switches of course. I can also home here too. I'm also not really using a full PID. I'm only using the proportional. I mean, these impulses from the motor come whizzing by, and in fact, about 1 inch of travel, I probably have 500,000 pulses. And if I shot by a little bit at the end, and it wouldn't be a problem. I mean, if it shoots too far, it's going to hit the hard switch and it's going to stop anyway. So I'm only using the proportional. That made it real easy. So this is the key. This is really the key that holds everything together. I cobbled this together out of steel, angle iron, and flat iron. This is the part that pivots. It's not in the end. It's kind of a third of the way up. I'll show you some other videos of it working here. But it confines the square tubing with all these bearings. I have bearings in the top, bearings in the side, bearings in the bottom, and I can position them just correctly. So there's a lot of movement, but not a lot of slop. And I am, like I said, I'm really impressed at how clean it makes these cuts. Here's a bottom picture of it. More bearings in the bottom because a lot more weight is on the bottom. Now, this shaft that comes through here looks like it goes all the way across. Of course, it does not. It terminates at these bearings on each side, and that's how it pivots. That's how the thing, tilts all the time. I got other holes here because this was originally my first prototype was kind of a walking beam thing, but that was putting too much arc in every cut. I did not like that, so I kind of scrapped that design and went to this one. Okay, this is a video. It shows you just a little bit of that tilting. Okay, not much there, but of course it will tilt up and tilt down if you're using a bigger, thicker, taller piece of stock to cut through. Okay, now here's the back piece. It's just a reciprocal wheel I put on here that's sort of like, I'm using a gear motor, 50 RPM. Because I've seen a lot of videos, people are trying to turn a hacksaw into a fast cutting device, and these things are just flailing away. And no, I remember my dad being nice and slow and true, and that's kind of what I went, and that's kind of what I got. So the the wheel I made is also PETG 3D printed. I got the maker motor. Here's the part number if anybody really is crazy enough to try this. But there's a hub on here. It's a 10mm hub. Double D that actually fits on, and of course I just matched up the holes, and it was not a problem, and really it's not been showing any stress or strain or wear. I think it's because I can slow it up when it does start struggling. It doesn't overwhelm things. The little projection here, that's something I don't use. When I was first thinking about this, I thought I might have to add a magnet to this and maybe a Hall effect or reed switch to count the reps, but I'm not using that at all. But this is similar to what I have on the other side. Although this one down here that holds the bolt for the bearings and all that, that's a lot more substantial. So that's not giving me any trouble. This is just a flat stock aluminum 1/8 inch I'm using for my drive piston rod. Plenty enough. This little device here, and I'll talk about this a little more in detail. This is my vibration sensor. This is what I use to sense that this machine is struggling and back off a little bit. So, and my first thing to overcome, I had to overcome several things to get this thing working. And the first thing I realized was this resolution of forces error. And the resolution of forces is that when two or more forces are affecting some direction. And of course I have the one force of it just going right into the material from the blade, and if I was cutting square stock, that'd been end of story. But unfortunately, because this is at an angle here, I saw that when the blade goes ahead and hasn't really started very well, it has a tendency to drag down that direction because that kind of falls away following that line. And if it ever did finally start over here someplace, it would not give me a very good cut. So I needed something to hold the blade where it needed to be until I got that groove started. So what I came up with was this. This basically, when I push the start button, the first thing that happens, there's a little servo here. I printed up a little servo arm on it, and that servo arm will turn around. It's got some bearings mounted on it, and that just holds the blade in place. And after, I don't know, X number of strokes, it will finally move away. It's actually hard coded into the software. Um, and that really took care of the problem. Okay, and after a way, like I said, it just sort of disappears. However, it also brought me a new problem. Is that this is the first time I've ever used a project that actually had a servo plus a motor controller using pulse width modulation. And I realized since they shared the same timer, there were some conflicts and a couple pins you couldn't use. So I had to kind of cobble things together and kind of change things around to get everything working. But they are now. I've not mounted the other servo on the other side, but I will if I ever have to cut the other miter there. But yeah, that actually has been that worked real slick. Now on the front, this is the front part that controls the dropping of the saw into the controls the feed rate basically. And again, PETG. This motor is actually was an additional motor I got with my Maslow CNC device. I liked the gears and everything, so I just went ahead and designed the gears for this. These are these 5/16 threaded rods. There's actually some hidden bolts or nuts in the bottom that really kind of tighten everything together. And since they're all moving in unison, I don't get any racking or anything. It just moves steadily up and down. You can't see, but there's some embedded high-grade nuts inside the 3D printing here that I kind of press fit in, and that drags it up and down. And also you can't see the bearings in here, but there's no 3D printed to metal contact. It's all sitting on bearings and rolling on that. And the top is not in the picture here, but there's also some bearings to the top that kind of hold the threaded rods in place and give them free motion and movement. There's my hard switch, which is adjustable if I really need it. I'm probably gonna set it and just forget it. But like I said, I got some soft switches, so if I figure it's close enough and realize through the encoder count it's getting close to zero, it'll stop then too. So this is the next problem I had. I noticed that when it's really started struggling on bigger pieces and flat pieces, I started getting a lot more vibration. And so I decided, well, I can use that vibration to tell me to slow up, stop the feed rate, so we'll just stop dropping the blade into the work and until things are cleared up, and then the vibration goes away and it continues to cut. So what you're looking at here, I mounted this piece of, this is actually one of the bronze welding rods for brazing or something. And there's a small little weight here I'm using, which is nothing more than a shaft coupler with a little bushing inside. And this thing, I can move that weight up and down and kind of tune the vibrations. And on the bottom, there's a little piece of copper. Okay, so the wire goes to the mill welding rod, and the other wire, of course, goes to the copper. And when they connect, it completes the circuit. And I know it's vibrating too much. So here's a video of it and working. And what you see here, this is the red light right here. That's actually telling me that the power's dropping the motor down. The minute the vibrations get too much, it just shut off. And so it's still sawing, of course, but it's not dropping in the material anymore. And so it's a set number of seconds. Basically, it looks again and it starts dropping in the material again. And if it's too much, it stops again. So that's that self-adjusting part. I have to say it works great. I was kind of pleased at how well that was. This is just a little 3D printed T, which I can adjust the size to it, the distance, the gap, I should say. But yeah, and the problem was, here's another problem, is that I've already used up my interrupts. Uno only has 2 interrupts, and they were used for the encoder. So, and as you saw how quickly those little impacts are, unless my program is actually looking right at that pin, if I was using an I/O pin for this, it probably wouldn't see that connection being made. So I needed to do something else. So I came up with this. This is the pulse stretcher. I kind of found a couple examples online and kind of put them together. And unfortunately, I don't have a schematic for this. I don't really do schematics anymore. I just sort of use my little board and plug things in until I get it working, and then just transfer that over to my PCB. But in a nutshell here, I have a 22 UF capacitor which will charge up through this relay network here. And what happens when that switch gets made here, it will suddenly quickly drain the capacitor down. And since the plus side of the capacitor is hooked right to the analog pin, my program basically just looks at the analog pin, and it will take however I have my pot up here set to my resistor. I can vary the resistance and tell it so that it charges up slower. It might take 2 seconds or so to finally slowly charge back up to full. And even the Arduino program, slow speed it has, if you give it 2 seconds to look at something, it'll just say, "Oh, look at that! It's actually dropped low. Time to shut it off." So it takes the place of an interrupt, but but it's not an interrupt. And again, I'm very happy with it. This is it right here. This is a pulse structure I had. This actually is a Cytron single motor controller. Over here is this little blue rectangle. That is a solid state relay. The motor itself on the saw motor is not controlled by a motor controller. It's just basically a solid state drive, turning it off, turning it on. And unfortunately, because when you turn it off, you have that magnetic flux collapsing down and creating a pulse. You can't see it, but there is a snubbing diode stuck in there basically to take care of that pulse. Otherwise, I think it would probably damage it probably would damage the relay over time. Arduino Uno with a shield I made. And when I'm doing this rat's nest prototyping like this, I'm not soldering things directly because like I said, I had to change things around because things are just being made, and it doesn't always come out the first time as you dream. And so I've been using a lot of these little screw-in terminals to connect things, and they work fine. This little device down here, that's the future when I'm going to switch to servo ones right versus servo left. So what side I'm actually using the servo on. This is my control box. It really controls the whole thing. In here, there's a little potentiometer with a detent. And if I turn it to the right, well, it raises the saw up. If I turn it to the left, it raises the saw down. If it's right in the middle of the detent, it stops. And I just map that out with the Arduino, how far it is in the middle one side of the other. It's kind of just a voltage divider. This button here is to start the saw or stop the saw. This button here, actually, it will save the EEPROM position. However, it also has a secondary feature. If this happens to be going down, the saw is lowering, and the button is pushed, that's the signal for the program to home. And it'll go all the way down to the homing switch, identify where it's at, and then raise back up, and that's basically your Z, where you're starting 0, bottom 0. I do have a 12 volt bus on here. 12 volt powers the saw motor directly. So it needs to be enclosed. I know that. It's just sort of, but I'm not going to do that yet. I'm just going to, I have a working prototype, and I'm going to work with it for a while. The thing that did kind of shock me, when I started this program, I didn't really think the software was going to grow as much as it did, but this thing is got pretty big, pretty fast, pretty complex, and very useful. Here's the back side of it. There's a side MD13S single motor controller. Backside solid state relay. I really like using solid state relays for such as this because they're just DC might arc a little bit too much at times, and this is great. This is actually the power supply. The power is to 5 volts, or actually 8 volts to the Uno, and then it uses the 5 volt controller on that. So this is the display, when it's done cutting. Okay, up to, that's my starting position, 573,114, and the error in this position, this basically was the overshoot. And overshoot, of course, error when it comes to CNC is how far away from the target you are. And so I don't really, like I said, these pulses are just whizzing by, and so you can get a lot of them very, very quickly, especially with a slow CPU that I'm using here. This is, if I save it though, so I'm going to push save. It's saved to EEPROM. Not sure why that's saying 259, but okay. I boot it back down, and 259 comes back up. That's actually the actual position where it's at. So and it kind of boots up and starts. Now, when it does boot back up, it's going to have a little bit different air. This air is now relation to the zero bottom. That's how far away it is from the very bottom when you're through cutting. So I have to say, oh, sorry, yeah, this is all DC powered too. I had this extra battery left over. I switched my GPS lawnmower over to lithium last year. Love it. And I had some of these incredibly heavy, deep cycle, very dirty batteries. And so I decided just in the way. So I mounted this on the cart so I can move the battery around too, out of the way. It's a big master switch and of course fuse protected and all that. But I mounted it on some little carts I got, and yeah, I'm kind of happy with the whole system here. But here's my take on my CNC hacksaw. I have a project I need, and so I decided, well, let's give this a whirl. I don't know if anybody wants these things. If you want the artwork for the printed circuit board, contact me. I can send it your way, even the software if you want. But this is such a unique, particular, specific thing that you got to be crazy if you want to make one of these. But more power to you. Anyway, hope this helps.